So one of the other things I just gave to you was a relationship between chemical potential, mu, and concentrations. And we didn't derive it. The derivation is on pages 417 to 19. It's in box 10.1. And we have the slides up here. I'm going to go through them rapidly. I strongly recommend not bothering taking notes. Just listen to it. Go back and read it if you're interested. If you don't care about the proof that this relationship is valid and you just want to use it, that's fine with me too. Okay? But I do want to talk about where it comes from briefly. But again, what this relationship is showing is that the difference in chemical potential would be the chemical potential of whatever it is. However I've defined inside, outside, 1 and 2, that information needs to be somewhere in my question, times gas constant, times the temperature, times the natural log of concentration, like I said, in region 2, part 2, wherever I am, over part 1. And if we want to put this in terms of standard state, if we want to let one of the conditions that we're looking at be standard state, we know that concentration at standard state is always 1 molar, so we kind of don't bother drawing that on the bottom. Okay. What was the standard state concentration for water? Yes. What? Sorry?
It's 55. I don't know if it's like lots.
55 molar is all we're going to use. Just 55 m is how we'll write it. So 55 molar is what we're going to use for our class is just standard state concentration of water. Okay. So like I said, here's the derivation of delta mu. I don't recommend trying to jot this all down. You have these slides. I gave them on Monday. I tacked them in. They'll be here again for you. Okay. So in this particular case, these drawings should look kind of familiar. Rather than being ideal gases, now we have some sort of solute in a solvent. Okay, but once again, we've divided our total volume into a grid, okay, or some sort of array. So in this case, we have a number of solute molecules A in 2 different regions of our solution. So region A has solute, is the red dots. Region 2, it's the same solute, still the red dots, but there's obviously way fewer. We can just visually see that. We also have some number of solvent molecules B. So the solvent is B, it's the blue dots in both cases, and we're making the assumption that we have way more solvent than solute, okay? And so this is the assumption we make in real life too. Our solvent's always water, and we always have way more water than we have of anything else we're interested in, okay? And so we're saying such that concentration of B never changes, okay? We have so much water that small fluctuations in reactions or other molecules won't change that water's at 55. And so we have the same number of sort of grid boxes in these two. We have our number of solvent molecules given by N sub B. Mu sub B would be the chemical potential of the solvent. We can have here mu sub A1 is chemical potential of A in this region and chemical potential of our A solute molecules in this region. And so free energy can be written like this for these 2 drawings. It's totally valid. Anytime you're asked for free energy, you could always write the Gibbs equation down. So we have G1 equals enthalpy 1 minus temperature times entropy 1. And so the next thing that we do is differentiate with respect to the number of molecules. So what's going on in this drawing here is, or this equation, is all of the terms have been, like I said, we've taken the derivative with respect to number of molecules N. So here it's number of solute molecules A in region 1. And the things that aren't changing are temp, pressure, and number of B, or the number of the water. And that's the same all the way through. And then in this case, we're dividing by the number of A-type molecules, but in region 2. Okay? And this term, this first term here, free energy, or like rate of change of free energy with respect to molecules, is the definition of chemical potential. Okay? So all we're doing is setting the right side equal to chemical potential of part 1. Okay? So mu for A1 is equal to this whole term here, mu for A2. So this is solute molecules. Remember, B is not changing at all. In region 2 is this side. Okay. We had an assumption last time, so we introduced something called ideal dilute solutions, okay? And this was, again, this assumption that we have way more solvent than we have solute. One of the other assumptions of that was that enthalpy doesn't change, okay? Entropy was the only thing changing. These molecules don't ever hit each other, interact with each other, any of that. So for an ideal dilute solution, the enthalpy changes would be the same in either region. There is no enthalpies the same in both, so we want to look at a difference. We want to calculate, we're trying to derive delta mu, so it would be mu2 minus mu1. But enthalpy in region 2 and enthalpy in region 1 are equal to each other based on our assumptions. So we can cross those terms out and simplify this to the difference in chemical potential will just be the entropy terms in the two different regions. And so in order to calculate these partial derivatives, we have to determine the entropy of our system. Thinking about these drawings, how do you get entropy? So multiplicity is one option. And again, when it's small enough, we can use multiplicity. The other thing that we can do here is, or the way this particular derivation goes through is using probabilistic definition. I can't stress enough that these are not energy levels here. I'm not saying that there's different energy levels. I'm simply saying there's three different categories: empty space, solute molecules, solvent molecules. It's just a poor choice of figure. Okay. But we can get the probabilities of each of the different types of molecules by looking at the total number of spaces we're filling. So this is now even more simplified from that other drawing, which was like a 13 by 13 grid. Here we just have 16 spaces, and we have, so many of them are empty, 3 of them have solute. I mean, obviously this isn't way more solvent than solute, but again, a simple setup. So for probabilistic definition, we could set up the probability of our 3 states. It would be the total number of solvent molecules over the total number of spaces we're filling. A is the total number of solute molecules over the total spaces we're filling. And empty is, of course, just going to be, 1 minus P1 and P2. So it sums to 1. Or we can say it's M minus these number of spaces is how much empty will be left over. And you can plug all of that in for all of the probabilities and sum over empty boxes, over our solute. This term drops out here because the probability of our solvent molecules here, or I'm sorry, here we're calculating entropy for our solute. We were just calculating entropy between the two positions for solute A1 or A2. Probability 2 is for our solvent, and it has no influence on this, so it drops out. Again, like I said, if you want to think through all the math of this, if you want to apply chain rule and product rule to break all of this down, I invite you to do it. Okay? It might be a good exercise for you to convince yourself that this makes sense and this is where it comes from. But what we can simply kind of jump all the way down to N sub B solvent is much, much greater than the number of solute molecules we have, so we basically just ignore the number of solute molecules because it's not affecting NB very much. Those terms all drop out. And what it ultimately brings us down to is that the change in chemical potential will be given by, so this came from probabilistic definition, right? KBT times the natural log of the number of solute molecules in region 2 over the total number of spaces we had. This is concentration. Okay? If you think of it as sort of mass over volume, if you will. Okay. And then this was region 1, and so this simplifies here. If we want to switch to molar units, we're using gas constant now. And all we've done to get to gas constant was multiply by Avogadro's number. Okay? Boltzmann times Avogadro's number was R. So chemical potential is proportional to the natural log of concentration. If the concentration in region 1 is greater than region 2, then when you take the natural log of C2 over C1, it will be less than 0. Okay? This number here will be less than 1. The natural log of something less than 1 is a negative number, so delta mu is negative. solute molecule in region 1 has higher chemical potential and higher concentration, will move spontaneously to region 2, the region with lower concentration. Like I said, looking at them visually, we already understood that. This proves that to us mathematically. Okay. And so the only thing I will just remind you is to think about when you're asked to calculate a change in chemical potential, watch for whether you're being asked for molecules or moles, watch for whether you're being asked to compare to standard state or two states, neither of which are standard state. Okay? So let's do an example problem. You will want this equation here. So if you haven't written it down, jot it down really quick before I put the problem up so that you guys can take a minute and work through it with the person next to you. Okay? So here we have the difference in chemical potential for a particular molecule between two regions of an ideal dilute solution is 5 kilojoules per mole. The region with the higher chemical potential has a concentration of 200 millimolar. What is the concentration of the molecule in the other region if we're at 293 Kelvin? Okay. So go ahead and work on that one for a minute or two, talk to the person next to you, and then I will go through the solution.